Okay. All right. Good afternoon, everyone, and welcome to Campus Lecture. And this is the first lecture of our 2025 to 2026 spring semester. And my name is Rebel, and then I'm one of the facilitators, and I'm here to introduce the speaker of the lecture today. So our speaker for today, Srikar, is a second-year graduate student focusing on experimental neutrino physics. He grew up in Orlando, Florida, and did his undergraduate study at the Georgia Institute of Technology, where he first started his research on neutrino detectors. Now he works with Professor Gabriel Ogen on the EOS and SNO plus experiments. In his free time, Srikar likes to read, climb, and doom scroll on his couch while relaxing with his cat. Very relatable. And please give our speaker a round of applause.
Hello, like I said, my name is Srikar. I'm very happy to be giving a Compass lecture. I'm giving the first one, and I'm not sure how I feel about that. I don't have to meet any high standards, and I get to set the standard, but I have no idea what to expect. So yeah, my talk is on ghost particles or neutrinos and how we actually catch them nowadays. I'm also going to be talking about some historical significance and why neutrinos are important. And if at any point someone has a question, please feel free to raise your hand or really just speak out. Same goes for on Zoom. Yeah, this is for a lot of people the first time they're going to be seeing some of the things that I'm talking about. So it's perfectly natural to ask any question. But yeah. So I included a slide that was, a little bit about me, and I'm realizing now that pretty much none of this information is new. The bio kind of just said it all. But I grew up in Orlando. I did my undergrad at Tech, and now I've been here for 2 years, and I'm working with that group right over there. And that's a photo from one of our collaboration meetings. Thought it'd be nice to also include a photo of my cat. She's really cute. It's on the couch. And I actually brought the laser pointer that I use with her. So that's what I'm going to be using through the talk. But yeah. Okay, so a little roadmap of what we're going to be talking about is, like I said, first I'm going to be talking about the history of neutrinos, and then why they could be useful for the future of physics as a whole. Once we get that context out of the way, we're going to talk about what actually produces the neutrinos that we're studying, and then how we detect them from a historical lens and for modern detectors. And then finally, I know it's getting around to that time. I'm going to share some tips for grad school or, in general, like what's after undergrad, whether that's in the industry or in academia. Okay. And like I said, if at any point you guys have questions, please feel free to ask. Okay, so I got into physics for a lot of the same reasons that you all did. And I'm sure to a lot of you, it kind of feels very satisfying to be playing with the puzzle that is the building blocks of the universe. From its most reductionist standpoint, you're trying to piece together why we have what we have here, why we experience life the way we do right now. So we do this with what we call the standard model. And the standard model is essentially a framework that hosts together that describes all the particles that we interact with, as well as the forces that mediate those interactions. And it's really good at what it's good at, and it's really bad at what it's bad at. It's really good for describing the phenomena that it's meant to describe, but it's too good. It's hard to fit in some of the pieces that we are currently trying to understand right now. For example, we have things like dark matter. We know dark matter exists, but we don't have a particle theory for dark matter experimentally confirmed yet. We have baryon asymmetry, so that refers to matter-antimatter asymmetry in a universe. We know there's antimatter. The Big Bang produces them in equal quantities. So why do we live in a matter-dominated universe right now? Last one is a quantized theory of gravity, but these are just some examples of things that don't quite fit into the picture of the standard model just yet, but that's what we're working on. And even the standard model that we have right now, there are still questions in the big puzzle. You can see the show up. Oh, fun thing. You can actually show different faces on this. So apparently I had that set to the face. But anyway, for neutrinos, which is kind of like this piece right here, we know neutrinos have mass, but we don't quite know why they have a mass. That's a big thing that still needs to be figured out. So what question did neutrinos solve? Well, a lot of them. But historically, neutrinos were postulated to solve the question of beta decay. So back in the 1920s, actually, let me talk about what beta decay is first. It's just a neutron decaying into a proton and emitting an electron. So back in the 1920s, there was a very good understanding of this process. Oh, sometimes we call the electrons betas. I'm going to be using that term interchangeably. It's confusing, let me know. Yeah, and in the 1920s, this was our understanding of how the process worked. Just a two-body decay. And you'll notice the charge is conserved here. That's important in a second. Now, there's an issue with this picture of beta decay in that if you've taken a special relativity class, then you would know that any two-body decay, well, the products of that decay are monoenergetic. They have a fixed energy, it's something that we can measure, but that's not what we saw in reality. So this red line corresponds to what we expected. In reality, we saw a distribution, and that corresponds to a three-body decay, not a two-body decay. So there's a third particle in here or there must be a third particle in here that would actually explain the energy spectrum of the electron. Okay. The other thing is, if you've taken quantum mechanics, you might notice that angular momentum isn't conserved in this process. Neutron is spin 1/2. Proton and electron are also both spin 1/2. So the right-hand side is a spin 1, spin 0, or spin 1 state. Angular momentum isn't conserved. So we need another particle to solve this picture. The issue is, with the particles that we knew at the time, there wasn't anything that could actually do that. So to understand the limits of what this new particle could be, well, if we take the mass of the neutron is heavier than the proton and the electron combined. That gives us a little bit of a freedom. The change of mass there is almost 1 mega electron volts. That means a new particle that would fit in beta decay has to be neutral, has to spin 1/2, and it has to have mass less than this. The issue is that particle didn't exist in the 1920s. So we have Wolfgang Pauli. He's a very famous, Austrian physicist. If taking quantum mechanics, you know about the Pauli spin matrices. Yeah. He postulated a particle with exactly the properties that I just said. And he predicted that it would have a mass similar to the mass of an electron. We know that's not the case nowadays, but give him credit for everything else. So the issue is, because this particle is neutral, because it's so small, it's really hard to detect. And Pauli himself was noted that there's a very famous quote where I'm not going to attempt to do a German accent or an Austrian accent, but you can read it. He's, worried about postulating a particle that can never be discovered. Of course, physicists love proving each other wrong. So in the 1950s, we went ahead and actually discovered the neutrino. And this is the first ever detection, or when I say discover, I mean detected. This later won the Nobel Prize in the late 20th century because of how meaningful it was, and just giving you an idea of how important neutrino physics is. But this is Cohen and Rhimes. This is Project Poltergeist. That's the beginning of that ghost particle moniker. But yeah, the way they did this is they took this large tank and they filled it with water. They placed it next to a nuclear reactor, and nuclear reactors produce a ton of neutrinos for reasons I'll talk about in a little bit. But what they're hoping for is they're hoping to see an anti-neutrino actually capture on a proton in a process called inverse beta decay. In that process, these two particles release or then become a neutron and a positron. So why this is relevant is because, well, we have two signals coming from this system. We have the neutron, which captures on hydrogen. So a proton of hydrogen captures the neutron, becomes a new atom, and it releases a gamma with a very fixed energy, 2.2 MeV. In addition, the positron annihilates one of the many electrons in water and produces two gammas as well. So this provides a very nice coincidence signal that's still being exploited in experiments to this day. And it was a good way of finding the neutrino. So, the first detection was back in the 1950s, and it's been a long time since then. And we've learned a lot about neutrinos so far. What do we know about them? Well, we know there are three flavors, three types of neutrinos, and these correspond to each of the leptons. So an electron has an electron neutrino, muon has a muon neutrino, tau has a tau neutrino, yada, yada, yada. They're chargeless, as Pauli postulated. They're chargeless, so they don't interact electromagnetically. They interact instead through what's called the weak nuclear force. In addition, they have a very, very low cross-section, 10 to the minus 43 meters squared. For context, that neutron capture process that we just talked about, the neutron capturing on hydrogen, has a cross-section of 10 to the minus 28. meters squared. So this is 15 orders of magnitude less likely for a neutrino to interact than it is for a neutron to capture on hydrogen. Of course, it still happens, which is why we see neutrinos, but yeah. I also want to point out in the top left corner of these particles, they have mass limits. We don't have a precise mass for the neutrino, and that mass isn't zero, even though in the standard model, we predict neutrinos have zero mass. We don't have an idea, or we have limits on the absolute masses of the neutrinos, but we haven't figured out the actual mass itself. Okay. Because they have mass, because it's non-zero, neutrinos undergo a process called oscillations. They're not the only particles to do this, but the three neutrino flavors can, they can oscillate between the flavors as they propagate. So what that looks like is, this is a chart, or this is a graph that shows a muon neutrino as it propagates some distance L. The probability, if you measure that neutrino again, the probability that it would show up as a muon neutrino, which is what the blue line is, or it could oscillate into a tau neutrino, which is what the red line, or it can oscillate into an electron neutrino, which is the green line. So if I was standing 500 kilometers away and I measured that singular neutrino, there's actually a higher chance that it's oscillated into a tau neutrino rather than a muon neutrino. So that's what we mean by neutrino oscillations. Okay. So the thing is, the neutrino oscillations, like I said, they happen because neutrinos have mass, but they're not sensitive to the absolute masses of the neutrinos. Instead, they're sensitive to these squared differences. So this is why we know that we know that neutrinos oscillate, and we can measure those oscillations, those probabilities, but we can't use that to get a scale for the absolute mass of the neutrino, rather just these differences. So, like I said, they don't probe absolute masses. And another complication is the second one, m2 squared minus m3 squared. We don't actually know the sign of that mass difference. We only know its magnitude. So, what do we know is we've set pretty good limits on, or not limits, we've made pretty good calculations, discovered, well, we have a good idea of what these differences actually are with pretty high precision. Notice for 3,2, it's just the absolute value. But the ambiguity of the sign of delta m squared 3,2 has led to the situation where we don't know what the heaviest neutrino is. So we labeled them 1, 2, 3, and you might be inclined to think that 1 is the lightest, 2, and then 3 is the heaviest. But that's not necessarily the case. With the values that we have, and the fact that we don't know this sign, we have this interesting issue called the neutrino. I don't know if it's called something, but the neutrino mass ordering is still an unsolved problem. With the numbers that we have, there are two different scenarios in which nu1 could be the lightest and nu3 the heaviest. We call this normal hierarchy, and that's probably what's more intuitive, just based on our numbering scheme. And we also have the inverted hierarchy, where now nu3 is actually the lightest neutrino. So that's a big problem, or that's a big open problem in neutrino physics. Okay, so we know neutrinos have a mass, but but let's talk about the origin of neutrino mass. Like I said, standard model predicts neutrinos to be massless. So let me take a step back and actually talk about fermions as a whole. Fermions are spin 1/2 particles, and they come in two types. We have what are called Dirac fermions. These are all of the fermions that we know right now. Electrons, muons, tauons, protons, these are all Dirac fermions. There's also another type called Majorana fermions. These are potentially neutrinos. These are massless fermions. That's why neutrinos potentially fall under that category. Majorana fermions also have a really interesting, and this is the guy that came up with this, and Ettore Majorana, very famous Italian physicist, mathematician. He also came up with a different mechanism that in which Majorana fermions could generate masses. That's called the Majorana mechanism. And none of the particles that we know, all the Dirac fermions, don't actually undergo the Majorana mechanism. They gain mass because of the Higgs boson, which is different than the way neutrinos would generate mass. That does pose a pretty interesting philosophical question in that why are neutrinos the only ones that undergo this mechanism? but that's a whole other thing. Majorana fermions also have a special property that they are their own antiparticles. Just really interesting to think about. There's not actually a distinction between nu E and anti-nu E. Okay, so my advisor, she really likes this image because it really shows, I don't know, it's kind of a cool artistic depiction of Majorana particles. I mean, you can see the white swans going towards the right and moving in the other direction in the negative space are the blue swans, and it really depends on the frame or the perspective that you're looking at. In which case, if neutrinos are Majorana particles, it really depends on what frame you're looking at them, whether they are neutrinos or antineutrinos. Okay, so if neutrinos are Majorana particles, they also undergo this really cool process called neutrinoless double beta decay. But first, let's talk about double beta decay. So I started this whole thing by talking about beta decay, but there are special isotopes where that can happen twice simultaneously, called double beta decay. Emits two betas and it emits two neutrinos. For a Majorana particle, if neutrinos are Majorana particles, we can see this, where there's no neutrinos associated with that decay. So a very common strategy to answer this question for neutrino masses is actually searching for this process right here. But it's a very, very rare process. The half-life for this is on the order of 10 to the 28 years. Put that in perspective, the age of the universe is on the order of billions of years. So this is much longer than the age of the universe. That doesn't mean we can't see it. I mean, we haven't, but let's really hope that means we still can see it somehow, because, it's what I'm working on. It's really hard to distinguish it. Yes.
Sorry, just going back to the previous slide. So
Yeah.
you said the neutrinos are their own antiparticles.
Yeah.
Is that something we know experimentally? Like, do we see
Ah.
neutrinos talking with each other? And
If we saw this, we would know it experimentally. But
Can you repeat the question for?
oh, yes. So the question was, if neutrinos are their own antiparticles, is that something that we can see experimentally?
Yes.
Is that
do we know it for sure, or is it just a theoretical prediction?
theoretical prediction right now? There's pretty high confidence that neutrinos are indeed Majorana particles, but like I said, neutrino double beta decay has not yet been seen. There are other ways that we can do this. The particles that undergo a double beta decay can undergo, or for various like nuclear isotopes, the branching ratios of the different decay mechanisms can depend on the Majorana nature of neutrinos. So not just through double beta decay, but you can also just look at decays as a whole. Yeah.
And if we were to detect double beta decay, like, would it be for certain, like, that the neutrinos would annihilate if they are Majorana particles, or is that like, there's still a chance that they wouldn't annihilate?
It would confirm, if the question was, if we do see neutrinoless double beta decay, does that confirm that there are?
No, like, is it 100% that they would annihilate with each other if they were Majorana particles? Or is there still like a chance that like?
Okay, so no, it's not 100%. If neutrinos are Majorana particles, you'll still see isotopes undergo beta decay.
Yeah.
So there's a very small fraction of double beta decays where the neutrino would annihilate with itself.
So it's not guaranteed that they annihilate.
Yeah, it's not guaranteed. It's guaranteed to have a non-zero probability, though. Yeah, so it will happen with enough decays with enough time. Yeah. Question.
How can we guarantee that we actually observe a double beta decay if neutrinos are so hard to detect? Like, how can we just not say, oh, we missed it, instead of saying, oh, it happened?
Yeah, so that goes into some detector design requirements. So you want to ensure you have a low background, because you don't want to mischaracterize events. So a lot of these experiments that look at double beta decay often happen very deep underground, so that you don't see cosmic rays coming from the sky, or people stomping their feet extra hard, and that's not background. And you also want really good energy resolution. So this plot kind of shows that, where in the red here you have the distribution of that's on the star, my bad. In the red, this is the normal double beta decay spectrum. This is the sum of the electron energies. That's what this plot is. You can see it's very broad, like that beta decay plot that I showed in the beginning. On the right here, this is the neutrinoless double beta decay peak. It's much smaller because it's less likely to happen. And in fact, this is actually an artist's depiction. The real spectrum is in this inset up here where there's a very large overlap. So the strategy here is you need a really good energy resolution to be able to get the energy or to reconstruct the energy of the decay right here rather than here, in which case you don't know. But if you see something happen out here, and if your energy resolution is small enough, then you can say with good confidence that it is right there, then you saw double beta decay. But there is with all the experiments that we've seen in the past, there's a very good chance that it's happened and we haven't seen it because detector capabilities, it just wasn't good enough at that time. But yeah.
This is going back to previous slide, but you mentioned something about the neutrino having cross section. But so it's a fundamental particle being treated as a point particle, right? Like neutron. But we also said that it's chargeless. So like in what sense, in what way does it have a cross section?
Yeah, so that's a really good point. I brought in some jargon and I didn't actually explain it. That's on me. So when we say cross section, despite the fact that, in most situations, cross section typically means, an area like this. This cross section actually is, when we say that in particle physics or nuclear physics, it's proportional to the probability of it happening. We say the word cross section because it has the same units as area. And historically, this was being used to talk about large nuclei in which it is useful to be thinking about an actual area. But yeah, we just say cross-section to mean probability essentially with some coefficients being multiplied. So that's why I say the cross-section for neutron capture is much, much higher. Therefore, it's equivalent to saying the probability of seeing neutron capture is much, much higher than a neutrino interaction. Yeah, good question. Anything else? Okay. So, yeah, so that's neutrino-less double beta decay. Okay, so I'm gonna breeze past this a little bit, but neutrino oscillations depend on this parameter. Oh my God, I keep fidgeting. I'm so sorry. Okay. Neutrino oscillations depend on this parameter called CP violation. This matrix, this very disgusting matrix, has a bunch of different parameters, and it essentially is the matrix that gives us the values for the probabilities for that big oscillation plot that we saw in the beginning. Changing this one thing like C23, or what that means is cosine theta 23, would just change the shape or, squish that graph a little bit or stretch it out. There's also this factor of delta CP tucked in here. What does that mean? Delta CP refers to CP violation. Essentially, CP violation is a measure of how antimatter and matter behave differently. So I think before people talk about CP violation, you often hear that antimatter is just matter with all the numbers reversed. It's instead of a +1 charge, you have a -1 charge. It's not necessary. Once you bring CP violation into the mix, now that's a measure of how particles and antiparticles behave differently in decays or interactions. We've already seen that CP violation exists for different particles. Delta CP here measures CP violation for neutrinos. So this is a measure of how neutrinos oscillate differently than antineutrinos. Now that's very small scale stuff, but in reality, that has a really big implication for the evolution of the universe. There's something called the Sakharov conditions, which are a set of conditions that could explain the matter-antimatter asymmetry that we see nowadays. Remember, that was one of the pieces that was floating off to the side in the beginning. It didn't fit into the jigsaw puzzle, but it might actually fit into the neutrino mass piece. So There are three set of conditions, but really the important one is the second one here, CP violation. So if we see CP violation for neutrinos, that could satisfy one of the conditions for the matter-antimatter asymmetry that we see here today. So very big implications, and it can be observed in oscillations, like I said. This is a plot that shows muon to electron neutrino transition probabilities, and these three different lines here just represent different delta CP values. You'll notice that the scale is very small. It's not close to that one that the previous one was. So it is very small differences, but it is measurable. And that's what the next set of experiments is hoping to be able to discern these three possibilities from each other. Yeah.
But if neutrinos are the antimatter, why do they keep up the CP violation?
That is a great question. And although it's trippy to think about, that's not actually mutually exclusive. Neutrinos could be their own antiparticles and yet still behave differently than the antiparticles. There's some heavy math involved in making that work. I'm not quite well versed in all that math myself, but it really depends on your frame of reference. So when you get into Q of T, everything depends, or there's a lot of things that depend on the frame of reference that you're measuring or you're doing your calculations. And when you change frames, you take into account CP violation as well as any flip between neutrinos and antineutrinos. But yeah, good luck figuring out that riddle. So yeah, that was a big background into the history of neutrinos and why they're actually useful, why they have large implications for the future of physics. I want to pause there and double check if we have any other questions on that. Yeah.
Maybe a quick one. I know it's oscillations, you said don't only occur for neutrinos. This is maybe a general oscillations question. But if particles are changing from one to another, which means they're changing their mass, does that mean there's some energy emission or absorption that is associated with that? And what does that look like?
Yeah, so it's not quite that they're, oh man, that's a good question. They don't absorb or emit photons to make that happen. Ooh, let me think. I think I need to parse that question a little bit more.
Sure.
Yeah. I'll come back to this. Yeah. And did you have a question as well?
I just want to make sure I heard you right. You said that the neutrino is its own antimatter, but behaves differently because it's antimatter in a different frame.
Yes.
Just wanted to make sure I got that right.
It is trippy. Yeah. So yeah, now I'm going to talk about neutrino sources. So where do we get all the neutrinos that we measure? There's a lot of them, just starting from, very early universe to sources inside our galaxy, outside our galaxy, on Earth. I want to touch on a few important ones. And if we have time, we can go back and start and talk about some other interesting ones. But the first one I want to talk about are reactor neutrinos. If you remember, Rowan and Kynes used reactor neutrinos for the first measurement or for the first detection of neutrinos. And we still use them to this day. A lot of nuclear processes emit neutrinos. For example, beta decay. Beta decay is a very common decay method, different than double beta decay. And we see that. We see a bunch of neutrinos coming from reactors. One experiment that actually utilizes is called Snow Plus. It's one of the ones I work on. And all the colors except for the orange one are the flux of neutrinos. So flux is just the number of neutrinos coming from the reactors surrounding Snow Plus. And I want to highlight something here. As you can see there, we have peaks, we have valleys, we have peaks here, we have valleys here. What is that? It's just neutrino oscillation. So Snow Plus can see neutrino oscillations coming from the reactors around them. Another really important one are solar neutrinos. They, again, the standard solar model is a bunch of nuclear processes that are happening in the core of the sun, emit a bunch of neutrinos. And this is how we actually first confirmed neutrino oscillations in the first place, measuring the flux coming from the sun. It emits a ton of them. So the flux coming from the sun is 10 to the 10 neutrinos per centimeter squared per second. So if you took very small region like this, literally the size of your thumbnail, there are 10 to the 10 neutrinos passing through here every second. It's a lot. Another very important one is called accelerator neutrinos. This is in particle accelerators, there's a lot of nuclear processes happening. Like I've said many times, they produce a ton of neutrinos. But nowadays, we're also building accelerators for the express purpose of measuring the neutrinos that beam produces. And there's a very big experiment happening in the US called the Dune experiment that utilizes this, but I'll talk about that in just a little bit. And the last thing that I wanted to touch on are galactic and extragalactic neutrinos, because this is what I did in undergrad and I made this talk, so I can talk about this. But all of these processes like supernova, black hole mergers, stars slamming into each other, they produce a ton of neutrinos, as well as a bunch of other things, charged particles, light. Because neutrinos interact so minimally, they actually are take a direct path straight to us. They're not, curved by any of the magnetic fields in space. They're not blocked by any debris or anything like that. And we can actually use the neutrinos as a probe of astronomical processes. This is the basis of multi-messenger astronomy or astroparticle physics. And it's also a very, very cool area of research. Okay, that's neutrino sources. Now we're going to move on to detectors, but I want to touch on something first, is the irony of neutrino detectors in the first place. So like I said, neutrinos are chargeless, and all the detectors that we use every day rely on electromagnetic interactions. Even, gravitational waves, they use lasers, so, an electromagnetic interaction. So there's actually no such thing as a neutrino detector. We're never detecting the neutrino itself. Instead, we're looking for the products of the interactions with neutrinos and matter. Take the Rowan and Kynes experiment, for example. We didn't detect the anti-electron neutrino. We detected the signal of the neutron being captured, and we detected the positron-electron annihilation. So we built detectors to look for the charged particles that come out of these reactions. And there are typically 3 modes of detection. All the detectors can be separated into 3 main classes. The first one are light-based detectors or optical detectors. The second are charge-based, and the third are heat-based detectors or calorimetric detectors. So I'm going to talk about each of these ones in turn here. So I'm going to start with light detectors because that's what I work on. And again, I made this talk. So yeah, charged particles emit 2 types of radiation, Cherenkov radiation and scintillation light. Cherenkov radiation, I'm sure you've all seen this picture or something like this picture before. It's a type of radiation that it has a very bluish characteristic glow. Scintillation light is something that we kind of manufacture ourselves, and it also emits a very cool light. So the light generated by these 2 mechanisms are collected by various different sensors, and depending on the experiment that you're working on, you can use PMTs, which are large and they collect a lot of light. SIPMs, which are very small, but they have really good timing and energy resolution. Or a burgeoning area of research is looking at these LEPPDs, which kind of try to get the best of both worlds, basically. So to talk a little bit about each one a little bit more. So Cherenkov radiation happens when a charged particle is moving faster than the speed of light in that material. It has to be in that material. And don't know why this animation isn't showing. Okay, there you go. So it creates, we have a charged particle moving in a line, and at every point it's emitting light, and it's moving faster than light in that medium, and it's creating a very standard conical shaped beam of light. This is very similar to a shock wave when you're coming to sound. Yeah, do you have a question?
Yeah, I was gonna ask how something can move faster than the speed of light, but then I think I maybe get it. Is it like it's moving, it's still moving like slower than the absolute speed of light, but it's like, it's not getting slowed down as much as the light is getting slowed down?
That's exactly right. So when we're dealing with water, it has an index of refraction of 1.33. So it has a speed of light that's less than 3 times 10 to the 8 meters per second. I did not remember what it was. And if a particle is moving faster than that, but still slower than the absolute speed, it can emit Cherenkov radiation. So Cherenkov light is very fast. It happens as soon as a particle enters a medium, and it's very directional. That cone that it produces is pointed in the same direction that the particle is traveling in. There are some very notable Cherenkov detectors. One is called SNO. Like I said, they confirm oscillations from solar neutrinos. See, it's really big. And another one is kind of I want to show you guys an inside view of what this looks like. This is the Super Kamiokande detector. Also very important, its predecessor, Kamiokande, provided a secondary confirmation of oscillations from atmospheric neutrinos. These two experiments shared the Nobel Prize for oscillations in 2015, I think. Yeah. And yeah, Super K is massive. But yeah. We can also see those Cherenkov cones or the Cherenkov, question.
Wait, sorry, no worries if you're like in a hurry, but like what were all these little like circle things?
Yeah, so these are actually the PMTs. So each of these PMTs are the light collection sensors, and they're each about this big. So you can imagine the scale of this experiment. Think about having all of those in one detector. Yeah, they get even bigger than this nowadays too. These are older.
And that's a whole person in a boat, right?
Yes, so this is, I don't know exactly what they were doing in this point, but for Snow Plus, which is the upgrade to Snow, they've had people inside the detector searching for leaks, like literally just kayaking inside the detector. They like look for a leak, and if they see it, they seal it up, and they're like, all right, get us out of here. And they get out. It's really cool. Yes.
Is it in the detector? It's mostly fluid.
Mm-hmm. Yeah, these are the light-based detectors are typically all fluid because they need to be very scalable. They need to be really big so that you have a lot of targets. Remember, neutrinos have a very low probability of reacting. So if you increase the number of targets, you're going to increase the number of expected events. So that's why a lot of the older detectors started off as water detectors. Water is much, much cheaper than liquid scintillator, which I'll talk about in a second. So yeah, these big ones started off as water detectors.
So, sorry.
No worries.
Does the instrumentation that you have give you a pretty not accurate, but like a good picture of like how it, because I attended a neutrinos talk, it's like they pass through your fingers. They mentioned something like that, and I was like, oh, how do you know that? It's like, does it give you an accurate picture of how it interacts with us?
With us.
Like the water. Sorry if that's a.
No, it's a good question.
You could answer it later too, but
I don't think it would do all that much, because if you compare the amounts of water that's in there compared to with the amount of water that's in your system, in your life you might undergo 3 or 4 neutrino interactions, at least from the sun. And all that is it would just produce a free electron in your body. And that happens all the time through beta decays or inverse beta decays in your body. So it's nothing that your body can't handle. It gets a lot more radiation from cosmic rays. So yeah. Maddie.
For super K or hyper K, you know, if they like purify the water, like kind of like you guys, but maybe not as much.
Yeah, so yeah, they have to go through a lot of purification process. And this goes back to your question, is they want to reduce their backgrounds as much as possible. And water has all the same radiation that, you know, everyday life has in terms of radon, uranium, thallium. So all these experiments have to go through pretty intense purification processes to cut down on those backgrounds. Yeah, okay. So that's Cherenkov. Oh, and then some pretty pictures. These are the actual Cherenkov rings. This is what we saw in Super Kamiokande. And with enough PMTs, you can actually get a very good picture of what's happening with the Cherenkov radiation. I also wanted to show one from the experiment that we have at Berkeley, is we can see these Cherenkov rings there as well. And both of these detectors are cylindrical, so you see the top and the bottom face kind of like folded out, and then the barrel of the detector is that. So that's Cherenkov radiation. And we also have scintillation, and it works a little differently. So scintillation isn't intrinsic to the particle. It's instead a medium that's manufactured. such that when ionizing matter goes through the scintillator, it deposits its energy in the scintillator. That medium then re-emits that light isotropically, and it is very bright. That's the key thing with scintillation light. It's very bright and very isotropic. And remember, Cherenkov light is conical, very forward pointing, whereas this is isotropic. The brightness is really important because when you're looking for these really low energy events like neutrinos double beta decay, you want to get as much light as possible so your signal to background ratio is much higher. You're getting a lot more signal with a bright scintillation. There are multiple, scintillators out there. You have plastic, like rigid ones. There's also liquid scintillators, and this is the thing that gets scaled. And this is the thing where you get a ton of liquid scintillator and you put it in a detector, and you're looking for signals from that. So some notable ones. There's one called Borexino, even though the B is being covered up. This was an Italian experiment. It has the most accurate measurements of solar processes. So it's a little bit after snow, but it's doing probes of the sun through their neutrinos. And there's also Snow Plus. This is the liquid scintillator upgrade to the snow experiment. They instead of looking at solar neutrinos, now they're looking for neutrinoless double beta decay, and they loaded the inside with a bunch of liquid scintillator. And as you can see, it's very, very bright. A very small source can illuminate the entire thing. Okay, and we're also working on something called hybrid detection at Berkeley. This is trying to get the best of both worlds. We're trying to get the directionality of Cherenkov radiation and the brightness of scintillation light. And this is the experiment that we're working on. It's a prototype, so it's a lot smaller than some of the other ones, but yeah, making good headway. There are three main principles that we're trying to leverage. I'm not going to dive into this too much, but yeah. The next, like I said, EOS is a demonstrator, and the next step is Thea, which is a much bigger version of this. So this one is, when I say comparable to the size of a human, it's, not actually, but it's an apt comparison when you've looked at some of the old photos. But this is a much, much bigger volume with the same principle, trying to get both types of light. So that's optical detectors. Now we're going to talk about charge-based detectors. Rather than looking at the radiation that's released by the charges, you're looking at the charge particle's trajectory, and you're trying to glean information about the events or about the particle from that. There are two main types in the past. In the past, we've had what are called bubble chambers or cloud chambers, tend to produce these really pretty images. Nowadays, a lot more modern charge-based detectors are called time projection chambers, which is a really cool name in my opinion. But yeah, we'll talk about both of these, starting with the bubble and cloud chambers. So what we do is we take this box and we fill it with like a liquid, typically like ethanol or some kind of alcohol, and we pressurize it and we raise the temperature such that it's right at that critical point between being a liquid and a gas. And as soon as any little bit of charged matter, charged radiation deposits a little energy, even a small kick in energy is enough to vaporize that the path that it travels along. Yeah, so I talked about that. The other thing that we do is we place this thing in a magnetic field. And the reason for that is because a magnetic field alters the trajectory of a charged particle. It makes it, a circular path. So from that, we can glean information about the particle's energy based on its radius of its bending, or also its sign, depending on if it's curving this way versus this way. Like I said, it produces very pretty images. And even in this one, you can see low energy electrons that curve around a lot because they have low energy. You can see higher energy electrons or muons, they still curve just a bit, but not nearly as much. And you also see these gaps between the trajectory here, between here and here, here and here. Remember, only charged particles will deposit their energy because they radiate. Neutral particles are essentially invisible to the bubble cloud chamber technique. So this is actually a neutral particle interacting, creating a charged particle, which then interacts and creates a neutral particle. So you can get all of that. I also want to include this, fun little piece of trivia. If you guys recognize this photo, this is the album cover for This Is It. Is This It by The Strokes? Really good album. It's also a bubble chamber image. This is taken from a bubble chamber at CERN. So yeah, really cool images. Yeah. The other type of charge-based detector is called a time projection chamber. This is essentially modern TPCs fill this detector with liquid argon, and I'll talk about why argon in just a second. But the idea here is that an event happens and it releases gammas, or releases light, as well as free electrons. Again, remember beta decay, there's an electron. Yeah, so that light, first off, it's very prompt because, light is fast. It hits a PMT, and what that does is that sets a time 0. The PMT sees light, it knows an event has happened, right? Now, the free electron then drifts against that electric field. If the electric field is pointed this way, towards the left, the electron is going to drift to the right into these collection planes, these wire planes. The wire planes record, the electron being hit against it at some time t. The x and y of where that event occurred is saved essentially by where it was hit on the wire planes. So the wire planes can glean XY information. And then you can use the difference of time divided by the speed of the electron, which some electrostatics, you can figure out its z position. That's why they call it a time projection chamber, because you're getting a time measurement based on you're using time, you're projecting time to get a z measurement. So why do we use liquid argon? Well, in reality, we could use any noble element. Argon is, cheaper and a lot more abundant. But if we use a noble element, that means the free electrons won't get recombined. Remember, noble elements have a full valence shell. They're very unlikely to pick up another free electron to create a new shell. So that's why we use liquid argon and not something like water or a liquid scintillator. Okay. All right.
That's a big one. Like we also use liquid xenon in many detectors, example xenon and elusive. And the advantage of argon is that we can do the discrimination, right, to clarify whether this is a background event or the target event more efficiently. And if we use xenon and other sense, we have other advantages, and argon is much cheaper, of course.
Yeah. They each have their own advantages, like you mentioned. There's a lot of experiments that use liquid xenon as well. The reason I'm talking about liquid argon is because it's an excellent segue into my next slide. The Dune experiment, which used liquid argon TPCs. So the Dune experiment is, in my opinion, kind of the future of particle physics centered in the US, at least. It's a very, very large facility for neutrino measurements. Dune is literally deep undergrad neutrino experiment, so it's focused on that. But the principle behind this experiment is that it's utilizing an a neutrino beam, basically using a particle accelerator to create a beam of neutrinos. So this is one of those interesting sources I was talking about. There are two sets of detectors. There's one set called a near detector that's close to the beam that measures the flux coming out of the beam. So that we can, rather than just a nominal picture of how the beam works, we can make measurements and see what's actually coming out of it. Then there's also a set of FAR detectors. Mine is actually where the FAR detector is going to be are in South Dakota, and the initial accelerators in Illinois and Fermilab, so very far apart from each other. And they're far apart from each other because then you can measure the oscillations of the neutrinos as they reach or as they propagate across this distance. And with that, you can get measurements of those mixing angles, measurements of CP violation, and the mass differences. So yeah, very, very big experiment happening in the US. It's actually timed really well for your guys' careers as well. If you do stay in academia, I'll get to that. There are 4 FAR detectors that compose the FAR detector set happening at Dune. The first 3 are guaranteed to be liquid argon TPCs. So TPCs are also a very big area of research, at least in the US, for neutrino physics. The 4th one is called the module of opportunity. Could be a liquid argon TPC. We are hoping that it's going to be the spot for DEA, which is the upgrade to EOS. And I mean, that's not confirmed yet, so it's just a hope, but we'll see what happens. The last type of detector is called heat-based or bolometric detectors. I'm doing really bad time, aren't I?
We have the room until 4:15. So
okay, wonderful.
time.
Yeah, bolometric detectors. Now, this is a really cool experiment and like detector principle, but it is so different than what I work on. I'm not going to be doing it justice in my talk right now. If you're interested in this, I would really, really recommend talking to the professor that works on bolometric detectors. But the idea here is it's a very small crystal, very, very low temperatures, like millikelvin. Yeah. And at that low temperature, it has a very low heat capacity. So any little bit of energy deposited, say by neutrino double beta decay, has a measurable temperature increase, very tiny energy deposition. Oh yeah. This is kind of an image of how that works. You have this. Have this crystal that also scintillates so that you get a nice coincidence. And with any little bit of energy release, you have a very sophisticated thermometer essentially read out the temperature increase. That part right there, the thermometer, is a very hardware intensive project. It's a very hardware intensive or like focused area of development. So if that's more your speed, this is a great area for you to get into because it's electronics operating at millikelvin temperatures and they need to be sensitive. They need to be able to, you know, distinguish what's happening here with even radiation coming from the sky. So that typically the two types of things that are used there are called TESs or NTDs. This is kind of more on the semiconductor side or more engineering side, but very, very cool pieces of technology, heavily reliant, I believe, on the Nobel Prize this year, actually, on Josephson junctions. But yeah, super cool stuff. And this is a picture of Cuore, one of the experiments. This is in Italy, actually, Gran Sasso, but each of these crystals is a neutrino double beta decay candidate, and it's also a bolometric detector itself. It's both of those things. It's both the target material and the detecting material. Super cool stuff. And I also wanted to point out, this is some parameters that was predicted by Cupid, or the upgrade for Cuore called Cupid. And notice this energy resolution, 5 keV. The energy deposition for neutrino double beta decay is on the order of 2.5 MeV. So this is an energy resolution of like 0.1%. That's really good. That's what these detectors excel at, is their energy resolution. So something like this, if a neutrino double beta decay event occurs, it's almost guaranteed to be able to distinguish it from double beta decay. So yeah, those are our bolometric detectors. So conclusions, neutrino physics, very active. Lots of cool implications for the future of physics as well. There are 3 detection modes, and there are many ways to get involved at Berkeley. So to highlight that a little bit, on the bottom here, I list 3 different people that work on detectors of each type of each mode. And honestly, the best way to get involved is to go to their office hours if you have a class with them. And honestly, just cold email them. I would manage your expectations because everyone gets a ton of emails, but that's the best way to get involved. Just reach out. Yeah. Yeah, so this is the advice for the future now. It feels weird to be like giving this because I still don't feel qualified to be able to provide advice, but I'll do my best. So I guess everything I say right now is pretty specific to, I mean, it's, it's stuff I got from my head. It's, based on my experience. And at least for me, I was really impressed on that. I kind of had to make a decision after my undergrad to either go into industry or academia, but that's really not the case right now. You don't have to make that decision right now. Sure, you can go into grad school, you can go into academia, but you can always just master out if you feel it's not right for you and find a job in the industry. Or you could complete the PhD, realize academia isn't the path for you, and then go into industry yourself. You don't have to worry. You're not making that big decision right now. You can wait at least 6 years and you're fine. Same thing for the industry. There are so many people in my cohort right now that are coming back for their PhD and in the cohorts around us as well. But a few tips if you do decide to go towards grad school. Oh, sorry, before I do that, do both. Like if you're about to graduate, kind of if your main plan is academia, have a backup as a job. Like, don't neglect that side of things. And if you're trying to get in a job, well, okay, I mean, if you're sure industry is the way for you, then, you know, do that. But like, if you're still on the fence, then still submit grad school applications. Like, nothing's really stopping you. But you know, if you do academia, vibe check your potential PIs. You're not joining a program for the name of the program. You're joining that place for its facilities or the person that you're going to be working with, as well as your life for the next 6 years. So, you know, those visitation weekends are very important. Do your research on potential PIs that you want to work with, not the schools you want to work at. That's the main reason I applied to Berkeley, was to work with the person I'm working with now, not because of the name of the Berkeley, which is a very spoiled thing for me to be able to say, but you know, it is true. I like my PI. Oh yeah, it's also the second one. The third one is, do not use AI to write all of your stuff. ChatGPT was so useful for my essays, but you have to use it like it's a tool, not as a writer. It's really easy to get into a rut, and you know, you're thinking of synonyms for words and you're thinking the same word over and over again. Like, how many times can you say the word unique over and over again? Use something like ChatGPT, or honestly, even start with Google first, to figure out those types of synonyms. If you're worried about your tone, give it 1 sentence or 2 sentences and ask, like, hey, what are some options to rewrite this with a better tone? It's a tool, it is not a writer. And it is also, in my opinion, a little naive to neglect it. You should. It's very powerful if you use it the right way. If you use it to write your entire essay, your tone is boring. Your tone is dead. Your tone is just way too professional for what this is supposed to be. You want to come off as enthusiastic for what you're doing. If you're doing a PhD, and you got to be really passionate about doing this, because, you know, for everything that we know, for everything that we've learned in undergrad, we probably could have a much better paying job in the industry, and our quality of life would be significantly higher. Not that it's bad right now, but it could be significantly higher. This is a passion thing for a lot of us. This is what we want to do. And you want to make that come across in your essay. Use only AI. That's not going to happen. So use it as a tool for very pointed and small changes at a time. Think hard about your rec letters. They say a lot about your work ethic and what you like to do. Okay. For industry, if you're going for a job, make a LinkedIn and go to career fairs. You don't have to do like those stupid thank you posts on LinkedIn. You don't have to do any of that. Literally just make one and put in your skills so that when people are searching up skills, your name shows up. That's it. That's you don't ever have to touch it. I haven't made a post in 7 years, and it's just doesn't matter. But yeah, develop your elevator pitch. You're doing physics. You're likely going to be applying to things like data science, engineering. You know, if you go into finance, there's that. Why should they hire you over someone who spent their undergraduate degree learning this stuff? It's because, you know, you're things like a quick learner, or you work very well in collaborative settings. There are very good reasons why your skill set as a physicist in your undergraduate degree work in these positions, and you have to make that clear in your elevator pitch. Oh yeah, and your resume is also very important, so spend a lot of time on that. That is actually something that AI is very useful for, is working on a good resume. Again, you don't want to sound dead or anything like that, but use it as a tool. In general, network, lean on your connections. I don't like the sentiment that I hear a lot in academia, that networking or using connections feels a little bit like nepotism. I don't like that. It's not. Like, ask your people to vouch for you. Ask your people to at least get a foot into the door, because if they agree to that, then it's not nepotism, because you've earned that that step. If they're putting their neck out for you, that means you've already proven to them that you deserve to put their own reputation at stake. That person is taking that step for you. They think that you are worth it. So it's lean on that. Like, these are people that know you very well. It's like the rec letters, but you know, the next level. And yeah, like I said, have a backup, keep both paths open. Also added my contact information there. If you have any questions, send me emails. My office is right across the hallway. I'm in there very sporadically, but you know, feel free to knock. If I'm there, I would love an excuse to not do my work. So yeah, that's it. Yeah. Sorry, I went a little over time, but.
Might have time for a couple questions, but only a couple, yeah.
Could you explain more on why like discovering CP violation would kind of solve the mystery of matter antimatter?
Okay, I was being a little, I was exaggerating a little bit. It's not necessarily going to solve it, but it has the potential to answer one of the conditions for the matter antimatter race. So baryon number violation is just a different kind of version of CP violation, different processes that can violate by baryon number. We also need CP violations because you need something where the matter and antimatter act differently. If they didn't, then it would all just annihilate. But if there's a process that generates matter in higher quantities than or higher rates than antimatter, well then all of a sudden, well, this is growing, but like faster. So even if they annihilate, there's still some matter left over. And that's exactly where we are right now. And then the third one is fluctuation out of equilibrium. Means, with the Big Bang, we were initially in thermal equilibrium. We are currently not in thermal equilibrium, so we need fluctuations out of that. So, yeah. Yeah, Maddie. Sorry.
A quick question, just, it was the neutrinos double beta decay that has an extremely long halfway. And does the regular double beta decay, like that's more common, or do we see that, or is it also like extremely rare?
It's pretty rare as well. It's not as rare. Its half-life is like 10 to the 22 years, like around there. So it's still very uncommon, but we see it in our detectors. Any neutrinoless double beta decay detector will see double beta decay as well, and at higher rates because half-life is shorter. Yeah.
I may have missed it, but what's the observations that lead to our prediction that neutrinos
Are Majorana?
Yeah.
It would be neutrinoless double beta decay. If we see it, then it's a confirmation that they're Majorana particles. Or there are also some isotopes that can undergo different decay rates, and those the relative rates between these different decay paths depend on its Majorana nature. So that can also be a probe of the Majorana nature of neutrinos as well. Yeah.
For the masses, for one of them, we have like a definite volume, but for the other, we just have a magnitude, right?
Yes. Yeah.
What's the reason then for the other, we just have the magnitude?
We just don't have the uncertainties for the experiments that we're measuring that are just too high to have that nailed down. But for the different cases, for the normal hierarchy, for the inverted hierarchy, we have different values for M32, but we can't distinguish between the two yet. The uncertainty is too high, basically.
We should hold there. Yes.
Okay.